Hello students, in our last two classes we have discussed about the physical characteristics, the order of the ionization energy, electronegativity, density of the group 17 elements. We have also discussed about the color of the group 17 elements. Mainly we have discussed for the halogens, that is fluorine, chlorine, bromine and iodine. And after that we have also discussed about the synthetic procedure for F2 and Cl2, their various types of the reactions and their uses. Then we have moved to the hydride and the oxides of the halogens. And now in our today's class I will start with the oxoacids of the halogens. So first of all we have to know what are the oxoacids of the halogens. Mainly the oxoacids of halogens that actually form with the halogen along with oxygen and hydrogen. Okay. So in case of fluorine it can form only one oxoacid, that is HOF. In case of bromine and iodine they can form three different types of oxoacids. For example, if I will take bromine, it can form HBr, HBrO3 and HBrO4, and if I will take iodine, it will form HOI, HiO3 and HiO4. But only Cl, that is only chlorine, it can form different types of the oxoacids, mainly four types of the oxoacids. That is HOCl, HClO2, HClO3 and HClO4. So what are the names of that oxoacids? So I am giving the example with Cl mainly. Suppose I have HOCl. So what is the name of that HOCl? HOCl is known as the hypochlorous acid. Next, HClO2. The name of the HClO2, that is chlorous acid. Chlorous, okay, that is chlorous acid. If I will go to HClO3, the name of the HClO3, that is chloric acid, and the name of HClO4, that is known as the perchloric acid. So fluorine, that actually form only one oxoacid, that is HOF. So what is the name of that HOF? The name of the HOF, that is hypofluorous acid. And in case of the chlorine, the four different types of oxoacids it can be formed, and the names of these oxoacids are hypochlorous acid, chlorous acid, chloric acid and perchloric acid. In case of bromine, the bromine can form three different types of oxoacids, and the names of these oxoacids are hypobromous acid, bromic acid and perbromic acid. In case of the iodine, it can form HOI, which is known as the hypoiodous acid. It can form HiO3, which is known as the iodic acid, and it can form HiO4, which is known as the periodic acid. So these types of the oxoacids it can be formed. Now, what is the bond strength? If I will take the example of the oxoacids of the chlorine, as because chlorine it can form the four types of the oxoacids, so we are taking the examples of the chlorine only. The bond strength of chlorine bond O, that actually follows in this order, that is OCl minus greater than ClO2 minus, greater than ClO3 minus, greater than ClO4 minus. That means in HOCl the ClO bond strength, that is maximum, and in case of the HClO4 the ClO bond strength, that is minimum. And if I will take about if I will say about the order of the chlorine oxygen bond energy, then we can tell that the HClO4 having the highest chlorine oxygen bond energy, and the HClO, that is the hypochlorous acid, the bond energy of Cl bond O, that is minimum. So why we are observe this type of the ClO bond energy? For this we have to draw the structures of the oxo acids. Okay, so if I will draw the structure of the HOCl, so that is the structure of the HOCl. If I will take the structure of the HClO2, so that is the structure of the HClO2, that is angular in shape. If I will take the HClO3, so this is the structure of the HClO3, which is mainly pyramidal in shape. And if I will take the structure of the HClO4, so that is the structure of the HClO4, and that is tetrahedral in structure. Okay. So if I will look the structure of these oxo acids, we can see that in case of the HClO4, the 3 double bonds are there in between chlorine and oxygen. Okay, 3 double bonds are there in HClO4, and 2 double bonds are there in case of the HClO3. 1 double bond is there in case of the HClO2, and no double bond is there in HOCl. So obviously the presence of double bond, that means the bond energy that should be maximum. So if a compound consists of triple bond or double bond, so obviously that bond energy should be higher than the single bond. So for that reason, when we are talking about the increasing or decreasing order of the ClO, in that case we can observe that the ClO bond energy, that is maximum for HClO4, due to the presence of 3 double bonds in between chlorine and oxygen, and it is decreased when we are going to HClO3 or HClO2, because in these two structures we can observe the 2 double bond and 1 double bond are there in HClO3 and HClO2, and the ClO bond energy is minimum in case of the HOCl, as because there is no double bond in between chlorine and oxygen. So that is the main reason for the ClO bond energy, and why in case of the HClO4, means in case of the perchloric acid, why the ClO bond energy is highest. Okay. So this is all about the oxo acids of the halogens. I think you guys understand these things. One point is also there when we are talking about that HClO4, which is mainly known as the perchloric acid, that actually dimerized due to the hydrogen bond. Hydrogen bond is there because OH is there. So due to the presence of that OH, it can be dimerized. It can form the hydrogen bond with the other molecule of the HClO4, and it finally dimerize, and its molecular structure is going to be increased, and its melting point or boiling point, that should be also increased in this case. Now we are going to the interhalogen compound. Okay, in my first class of group 17 elements, we have already discussed about the interhalogen compound. So what are these interhalogen compound? In case of the interhalogen compound, mainly 2 different types of halogen atom should be there, and that is mainly known as the interhalogen. For example, ClF, BrF5, IF7. So these are the example of the interhalogen compound. So that now we are talking about the few features of that interhalogen compounds. The interhalogen compounds, these are all covalent in nature. So there is no ionic bonding, or there is no ionic interaction. So all interhalogen compounds, they are covalent in nature and they are diamagnetic. okay, and they are diamagnetic, and they are volatile, solid or liquid except ClF, which is gas at room temperature. So all interhalogen compounds, they are volatile solid or volatile liquid except only one interhalogen compound, that is ClF, which is a gas at room temperature. The interhalogen compounds are more reactive than the halogen because the X dash bond, suppose I am taking the ClF, so in that case the Cl bond F, that bond that is weaker than the XX bond, means Cl bond or FF bond. Okay, so for that reason the interhalogen compounds are very reactive than the halogen, as because in interhalogen compounds the difference in electronegativity is there, so there is a ionic separation in case of the interhalogen compounds, and for that reason it is more reactive than the simple halogen like chlorine, bromine or iodine. One exception is there, that is fluorine, as because everybody we know that fluorine is very reactive, and so for that reason the fluorine, except fluorine, all other interhalogen compounds, they are very reactive than the halogens. Next we are going to the reaction part. Suppose the XX dash, that is the interhalogen compound, and when it reacts with the water it will form HX dash and HOX. Why it will form HX dash? Here I have written over the X dash, that is the del minus, and over the X, that is del plus, which means that the X dash, that is more electronegative in nature than X. Okay, so when the X dash is more electronegative, so obviously over the X dash the more amount of electron density should be there, and when it reacts with the water it will take the hydrogen, because hydrogen is positive and OH minus, that is negative, and for that reason if the electronegativity of X dash is more than the X, and when it reacts with the water it will form HX dash and HOX. Again, if I will take another interhalogen compound like X3 dash, and when it reacts with water it will form HX dash plus HOXO, which is known as the halite, T. Okay, halite. Again, if I will take X5 dash, and when it reacts with water it will form HX dash along with HOXO2, which is known as the halate. If I will take X7 dash like IF7, and when it reacts with the water it will form HX dash along with HXO4, which is known as the perhalate. Okay, so these are the different types of the reactions of the interhalogen compounds with water. Now if I will look the structure of the interhalogen compounds, you can draw the structure by using the VSEPR obviously, and by using the VSEPR we can we can observe that the shape of the XX3, that is bent T-shaped, the structure of the XX5, that is square pyramidal in nature, and in case of the XX7, that is pentagonal bipyramidal in structure. Now we are going to the synthesis of the interhalogen compounds. We can easily synthesize the interhalogen compounds. For example, suppose I have chlorine and fluorine, and if I will take both chlorine and fluorine in 1:1 volume by volume ratio, and if I will react both chlorine and fluorine at 437 Kelvin, it will form ClF. More reactions for the synthesis of the interhalogens are also there, like when the iodine and chlorine reacts together and the amount of chlorine is in excess, then it will form ICl3. Similarly, when the chlorine and F2 reacts at 473 Kelvin, it will form ClF3. Bromine and F2, it will form BrF3. I2 and Cl2, it will form ICl. Bromine and F2, it will form BrF5. So in this way we can easily synthesize the different types of the interhalogen compounds, and we had also observed the reactions of the interhalogen compounds with water, and also we have discussed about the structure of the interhalogen compounds and their physical characteristics, like their covalent in nature, they are diamagnetic. In maximum cases, the interhalogen compounds are volatile, solid or liquid, and these interhalogen compounds are very reactive than the halogen. This is mainly due to the difference in electronegativity in the interhalogen compound. So for these reasons, the interhalogen compounds are more reactive than the simple halogen molecules. Next, we are going to the minerals containing the halogens. So many minerals are there containing with the halogens, but mainly we are talking about very simple and very well known minerals here, like rock salt. Everybody we know about the rock salt, that is actually NaCl, that is sodium chloride. So that is one type of the mineral, and that mineral is commonly known as the rock salt. Another one is the horn silver. Horn silver is the mineral, and that is actually AgCl, that is the silver chloride. Another mineral is also there like sylvine. Sylvine is the KCl, and another one is also there, that is kernelite. Kernelite, which is KCl, .NgCl2, .6H2. So these are very famous, very well known minerals consisting of the halogens. Next, almost we are at the end of the group 17 elements. Now I will discuss about the bleaching powder or the chloride of lime. Okay, so the bleaching powder that can be manufactured in batchman's plant. So the bleaching powder that can be synthesized or that can be manufactured in the batchman's plant. So here I am mainly talking about the industrial preparation of the bleaching powder, where the chlorine gas is passed into dry slacked lime. So these reaction I have already discussed in my last class. Okay, so if you want to check the synthetic procedure of the bleaching powder, you just look the video of my last lecture, where I have already told about the synthetic procedure for the bleaching powder, where the chlorine gas is passed over the dry slacked lime, that is calcium hydroxide. The bleaching powder, that is yellowish white powder with the smell of the chlorine, and most of it's soluble in water, but a small amount of the insoluble lime. So now we are going to the reaction part of the bleaching powder. Bleaching powder, when it reacts with the insufficient dilute acid, it first forms the HOCl and finally releases the oxygen, and for that reason that actually acts as a good oxidizing agent, as because it liberates also the nascent oxygen. Okay, so when the bleaching powder, that is mainly the COCl and other impurities are also there, that actually I have discussed in my last class. You can see from my last class. So mainly the COCl, that is calcium chlorohypochlorite, reacts with the H2SO4. Mainly it will form calcium sulfate, calcium chloride, HCl, and the oxygen. Okay, and with the excess of the dilute acid, it releases the Cl2 gas, which is also known as the available chlorine. Okay, so when the bleaching powder reacts with the excess, means the sufficient amount of the dilute acid, like H2SO4, it releases the chlorine gas, and that is known as the available chlorine. So the reaction, that is COCl, when it reacts with H2SO4, it will form CaSO4, water, and Cl2, and again that COCl react with the carbon dioxide, which is mainly in the atmosphere. It will form calcium carbonate along with the chlorine. So that chlorine is known as the available chlorine. Next reaction, that is known as the auto-oxidation reaction, that actually happens in air. So if I will stand the bleaching powder for a long time in air, it decomposes and loses its bleaching property. That is mainly due to the reaction, that is when the COClCl, if I will stand the COClCl for a long time in air, it will form CaCl2 along with CaClO3 whole 2. Catalytic decomposition reaction, that is when I have the COClCl and if I will give a very small amount, that is very small amount means the catalytic amount of the cobalt chloride, that is COCl2, then it can be decomposed to form CaCl2, that is calcium chloride along with the oxygen. The bleaching powder, it can react with the cold water and it mainly form the calcium 2 plus, Cl minus and ClO minus, and when it reacts with the hot water, then the ClO minus that actually decomposed to ClO3 minus and 2Cl minus, and that reaction is known as the auto-oxidation reaction. So it can be reacted with the cold water along with the hot water, and in the other reaction you had also seen that it can be reacted with the insufficient amount of the dilute acid, and if I will give more amount of the dilute acid, then it will give the chlorine. So if the less amount of acid is there, then it will give oxygen, and if I have more amount of acid and when it reacts with the bleaching powder, it will give the chlorine gas, which is known as the available chlorine. It also shows the oxidizing property, that is if I have the C2H5OH, that is the ethanol, and if I will give very small amount of the bleaching powder, that actually gives the nascent oxygen. So the ethanol, it can be oxidized through the acetaldehyde, that is CH2CHO. Moreover, in the same reaction condition, if I will give the COClCl for long time, then the ethanol, it can be formed the chloroform, that is CHCl3. Okay, and finally we are giving the two short note to start topic, that is the NaOCl, which is also known as the liquid bleach, and the anhydride of the perchloric acid, that is HClO4. Everybody we know that perchloric acid I have already discussed in this class in oxo acid, in oxyacid portion, that is perchloric acid, that is HClO4. So if I will hit the HClO4, then it will form the Cl2O7. That's why the Cl2O7, that is mainly known as the anhydride of the perchloric acid. So in our today's class, mainly I have discussed about the oxo acids of the halogens. Mainly the chlorine atom, it can form 4 different type of the oxo acid, like hypochlorous acid, chlorous acid, chloric acid and perchloric acid, and we have also observed the structure of them, and from these structures we can say that the bond energy, the ClO bond energy, that is maximum in case of the perchloric acid. Next, the few features of interhalogen compound we had observed. The reactions of that interhalogen compounds with water, they are covalent in nature, they are diamagnetic in nature, and they are more reactive than the halogen, and what is the reason behind it, these things I have discussed in my class today. And then finally we have also discussed about the synthetic procedure for the synthesis of the interhalogens, then few well-known minerals like rock salt, horn silver, sylvine and kernelite, these things I have discussed. And then finally the bleaching powder, the synthesis of the bleaching powder, and then the reactions of the bleaching powder, what is the available chlorine and how bleaching powder reacts with minimum amount of dilute acid in maximum amount of dilute acid, and how the bleaching powder reacts with the cold water, how it reacts with the hot water, how it can be decomposed in presence of the COCl2, and how it can be oxidized, means how the auto-oxidation actually takes place in case of the bleaching powder. These things I had discussed. And last, the oxidizing property, like it can oxidize the organic molecule like ethanol to acetaldehyde or ethanol to chloroform very easily due to the presence of the nascent oxygen. So this is all about our group 17 elements. Okay, so thanks to all of you.